Good morning, Copenhagen, and welcome to NDC. My name is Damjan, and I'm running a small London-based consultancy, helping our clients get up to speed with modern trends in web development. We pretty much do all things web. If you want to get in touch with me, you can do that via email, or you can also follow me on Twitter if email's too personal. If you actually check my Twitter profile, it'll appear that I never tweet anything because there doesn't seem to be any tweets, but that's actually not true because I'm Serbian originally, and Serbian people aren't scared of anything apart from three things: the draft, uniformed people, and the Big Brother. So every now and then, periodically, I always delete all of my tweets from my Twitter account, so my followers only have like a sort of limited window of opportunity to kind of see my tweets and the stuff that I retweet. Which is actually quite interesting because if you go on my Twitter page, you get to see this. Can anyone spot the problem maybe here? Maybe the font is too small, but there is something weird on my Twitter profile. Anyone with good eyes? They can see a problem. No? Okay. What's the problem? Okay. But there aren't any. Yes, exactly. Okay. So basically it says that I have 7 tweets altogether, but there aren't any. And apart from me being Serbian, I'm also suffering from heavy OCPD. So I'm really annoyed by this. And then I Googled for it and found out that this is actually by design. Basically, they say if you ever deleted a bunch of tweets, your tweet counter might not be correct. And that really annoyed me, and because they said you can get in touch with our customer service representative and they'll be able to fix the problem for you, which I did 2 years ago. And they still haven't come back to me. So I still have these 7 phantom tweets on my account. And I really find it absolutely fascinating that in 2019 AD, we have all these cloud formation templates and Kubernetes and Docker containers and web scale stuff, MongoDB, and the computers cannot count correctly from 0 to 0. That is absolutely fascinating. But I don't actually think that's unexpected. I think that's actually a perfectly normal thing in sort of today's day and age. And it's all to do with what is called a climax design theorem. It is from a book by John Gall called The Systems Bible. It's actually a really interesting book to read. It's a very short book. I really like short books. So you can read it in like a couple of days. And one of the things that he says in this book is that a large system produced by expanding the dimensions of a smaller system does not behave like the smaller system. So basically, if you take a reasonably sized system and then just make it bigger, the system just stops behaving as the original one. Like things just don't scale. Normal systems in nature just do not scale that way. And I'll give you a couple of examples. So the first one, and my favorite one, is about the space vehicle preparation shed. I quite like the name shed, okay? Which turns out to be the largest man-made building in the world. And its only purpose in life is to sort of protect the space rockets from the elements. But it turns out that the building is so large that it has its own climate. So it has like clouds and rain in there. So it basically pellets the rockets with storms of its own, even though it's designed to protect them from the weather. Another one is about this ocean liner, the Queen Elizabeth II, which is the largest ocean liner ever built. And for the purpose of safety and reliability, it has 3 separate boilers. And on a recent cruise, in perfect weather conditions and calm sea, all 3 of them failed simultaneously. And the last one is about this largest telescope, optical telescope in the world. It's the 230-inch, it's got like this 230-inch reflector, a massive, massive mirror, so that you can focus things really, really clearly. But the problem is, it takes a really long time to reach the thermal equilibrium, basically to settle due to the thermal expansion and contraction. And by the time it reaches the equilibrium, the night is over. So basically, you cannot use it. It is so large that it cannot be used at all because it never reaches the thermal equilibrium. And things also work the same way, the other way around. So if you start making things smaller and smaller, you also hit a different kind of problems because the systems don't scale that way either. If you have some abstractions that work on scale x, they don't really work well on scale 1000 times x and also x divided by 1000. And there's this really amazing talk, I think it was actually 1959, by Richard Feynman. And it was actually a lecture, a public lecture, and it was called "There's Plenty of Room at the Bottom." And at the time, it didn't kind of raise any interest. Like, people weren't really fascinated by that. But I urge you to watch the lecture. It's absolutely mind-blowing how clever the guy was and the ideas that he had. And basically, the whole talk revolves around trying to make smaller and smaller machines. I don't know if you ever used pantograph when you were kids. So those were basically the machines where you could paint over a certain picture and then set the scale, and then it would make the picture, twice as big or half the size of the original one, and so on. So basically, his idea was to build a human hand at like half the scale, and then use these to build even smaller hands, and then use these to build even smaller ones, and so on, all the way to sort of microscopic level. So rather than kind of using chemistry to create and synthesize small things, use some sort of machinery that just is recursively built to be smaller and smaller. And then he sort of predicted that there would be some problems if you try to do this. And he says, as the sizes got smaller, one would have to redesign some tools because the relative strength of various forces would change. Although gravity would become unimportant, surface tension would become more important. So on different scales, different forces come to play. Like when you have the macro scale, gravity is really powerful force, but on the microscopic level, you can completely neglect the gravity. So, if your project manager ever comes back to you and says, "Oh yes, yesterday I watched this really cool documentary about the gravity and the planets," and that's actually amazing. Like, they're never late. They always have really predictable trajectories. And everything just runs like the clockwork. There's no probability involved. There's no chance. Everything is really, really deterministic and determined. Like, why can't we have that on like microscopic scale? Why can't we have our quantum devices working like that? Well, you can't because these forces just don't come into play on such small scales. So, and this is actually really interesting. Because if we go back to the sort of very beginnings of the general purpose computing and the von Neumann architecture, we'll see that initially we had some physical constraints about the size of the system that we were capable of building. And that sort of also implied the size of the problems that we could solve and the size of the programs that we could write and we could build. So, for example, the very first general-purpose computer, programmable computer, called ENIAC, had 20,000 vacuum tubes. And by design, a few of them were always broken. Like when you have 20,000 of them, a few of them would just be broken by design all the time, like 3 or 5 or 10 or however many. And then one of the really important problems at the time was whether it's possible or not to design a reliable system from unreliable components. Like you had these unreliable components like vacuum tubes, but is there a way to kind of cleverly combine them in such a way so that even though they are individually unreliable, that the system, when you build, becomes a reliable system? And this guy, John von Neumann, whose actually real name was János Lajos Neumann, or Neumann János Lajos, because he was Austrian, or Austro-Hungarian, he sort of mathematically proved that this thing is possible. So even with unreliable components, you can still make reliable systems. But then, at some point, after that, transistors were invented, and then this problem has just gone away. There was no need for designing systems in such a way because the components were inherently reliable. Which is actually really interesting from today's perspective, because whatever was old is now new, and whatever was new is now old again. So now we have these clouds. We have those general purpose cloud infrastructure that is composed of unreliable components, like each of the machines, individual machines in the cloud might go up and down at any point in time, and we really don't have a control over that and when that happens. But we're still trying to design and build reliable systems around that constraint. So even though this art of making reliable things of unreliable components, there was a long period of time when that was not needed. That obviously is becoming more and more important in recent years. And it's same with like functional programming. Like functional programming was sort of on the margins of computing sciences and studies, but it's becoming more and more fashionable in recent years. So I really like to kind of put things in perspective and really like history and sort of anniversaries. And 2019 is actually a brilliant year for anniversaries. I'm really blessed that today is 2019 because there's so many important anniversaries this year. And in my opinion, it is actually 50 years ago, in 1969, that was, I think, one of the most important years in the history of humankind, in history of human civilization. Can you maybe name one of the things that happened in 1969? I guess you're too young, but maybe one big thing. No? Okay, Apollo 11, the moon landing. Yes, definitely. So basically, that's the kind of ultimate accomplishment in the human exploration. It's the very first time that a human species has set foot on a thing that's not Earth. Yes. Another important thing that happened in 1969 is also the very first ARPANET link was established. And ARPANET is like the precursor of today's internet. And it's absolutely mind-boggling that today some child in Africa might have access to more information than, I don't know, the president of the most powerful country in the world 30 years ago. Apollo 11 and discovery, and also some kind of freedoms and social political things like, Woodstock, Summer of Love, end of the 60s. If you're into music, I think Beatles released their last studio album, the Abbey Road, which I think is the best Beatles album. And they also had the last public performance. If you're into football, Pelé scored the 1,000th goal of his career as well. But it's not actually 1969 that is going to be important for me. It's going to be the 1869 instead. And it's in 1869, exactly approximately 150 years ago, that Dmitry Ivanovich Mendeleev released the very first version of the periodic table of elements. It didn't look like today's one. It was actually rotated by 90 degrees, so you probably wouldn't recognize it as such. But I think this was sort of a monumental accomplishment and a monumental achievement. So the same way in 100 years later, the kind of three things converged into one, like the kind of age of discovery, the age of communication, so we are kind of closer together and communicate better, and all those civil liberties. In 1869, we finally kind of got a grip on what the stuff around us is made from. This is like the breakthrough year for chemistry. When I was a student, I never really enjoyed chemistry, but later on I really learned to appreciate it, especially the chemistry from that era, because I think the guys that did chemistry at that time were the sort of ultimate developers, ultimate debuggers. They were capable of deciphering the secrets of the microscopic world by running experiments and using really, really primitive tools. So chemistry was just a sort of a window into all this intricate behavior of the quantum mechanics. And they managed to work out the fine structure of the stuff that surrounds us by using very primitive tools and kind of running limited set of experiments, which is literally what sort of black box debugging is all about. Like you have a system, you put some inputs here, you observe some outputs, you have no idea about the mechanics of what's happening inside the system, but by running sufficient number of those experiments, you can actually get a pretty close idea of how the system works and what is it actually composed of. So what's all this sort of chemistry stuff about? Well, it's about what stuff is made of, like what are these particles, these discrete particles that consist the matter around us, what are their properties? Like they managed to sort of make a catalog of all the chemical elements that exist and list their properties. And then that allows you to build new stuff in a predictable way, because if you understand the properties of these elements, then you no longer have to have blind experiments and let's try and mix this with that. You can make some predictions of what happens if I combine A with B or B with C or C with D, which is sort of very, very similar to computer programming. And then we can ask a sort of similar question, like what are computer programs made of? Like if we look into a typical JavaScript program, we'll see lots of different things. We'll see what we call values, things like numbers, booleans, strings, objects, arrays, and functions. We also see different operators like plus, minus, multiplication, and so on. We see the flow control statements like for loops, if statements, and switch statements. Modern JavaScript also has classes, so those are some other artifacts that we can use, and many more. And then the question is, do all these things overlap a little bit? Like, would it be possible to accomplish the same type of computations, basically perform the same type of computations that we can do with all these artifacts, but by using a much smaller set of features? Like, what are those discrete elementary particles that we can use to compose any kind of JavaScript program and make any sort of computation? And then, obviously, because this is not real world, this is some make-believe imaginary thing. Depending on who you ask, you might get different answers. So some people would just be satisfied by saying, well, it's all just ones and zeros. all you need is a kind of sufficient stream of ones and zeros, and that can represent any program and any piece of information and any computation, because that's what it ultimately comes down to. The other option is to use, I'm going to call it JsFlip, but it has much more colorful name. Our basic idea is that you can reduce all of JavaScript to just these 6 characters. So any program that you can build in JavaScript, you can actually implement just by using these 6 characters. It is basically something that you know, one of those incredibly smart and annoying kids in a classroom would come up with when you give them a task like this. So it's abusing the kind of type inference rules in JavaScript and the kind of quirks of operations and the fact that JavaScript is loosely typed language. I can actually show you a little example of a program in, let's call it JsFlip. You probably cannot see this, but this program is about 120 kilobytes long. So there's 120K of stuff like this. So it's just a repetition of these 6 symbols. And hopefully, if I take this and then paste it in Chrome DevTools and then run it, it's going to take a while. We get this. I'm going to do it the other way around. I'm going to make it bigger first and then paste it. Okay. So basically, that was a FizzBuzz implementation in JsFlip. Only by using those six characters, you get this program that you know, prints fizz if it's divisible by 3, buzz if it's divisible by 5, or FizzBuzz if it's divisible by 15. But that's not really what I'm after. I want something else, because these primitives, they don't really scale well. It's not something that you could use to build an application and reason about the application that you're building. It's basically just a gimmick to encode every JavaScript program using those six characters. So to do that, let's look into values. We already mentioned values as one of the primitives that we can use in the language. So what is a value? What are values? And what we can do with them? So we can store values in constants or in variables, like this. So we have this string value, which we can store into this variable or constant called v. We can also make values the values of certain property of an object in JavaScript. So here we have an object and a reference to that object called person stored into a variable. And then we have this value being the value of a property called the name of this object. So here we actually have two values. One is the object and the other one is this string value, which is the value of a property called name of this object. We can also store them in arrays. So here we have an array, and then one of the elements of this array is this string value. We can pass them to functions. So any kind of value that you have, you can pass as a parameter to a function and then get some sort of result back. And finally, we can return values as the result of function applications or function invocations. So when you invoke a function, that function can return a value. And what is really important is that in JavaScript, functions are actually values, and we can do with functions all these things that we just seen that we can do with the string. So basically, there's a perfect symmetry between all the different types of values. Whatever you can do with one, you can do with the other as well. There's no like special cases or special treatment. So, for example, the only extra thing that we can do with functions, so this is what makes functions special, is that we can apply them, or we can invoke them, or we can call them, however you call this. And for the purpose of this abstraction, functions are like boxes. So function is just a black box where you provide some inputs. The function does something to those inputs and then return an output as a result. And you pass the inputs as parameters, and you capture the result by capturing the return value of a function. And because functions are values, we call them we say that in JavaScript they are first-class citizens or first-class values because they're equivalent to all the other values. And if you kind of look into this feature of the language a little bit and sort of investigate, you'll see that that's not an easy problem to solve. And that's why not all programming languages support functions as first-class citizens, because it's tricky to solve the so-called fun-arg problem. And the fun-arg problem is being able to pass functions as parameters to other functions and return functions as results of other function invocation. So let's just briefly go over function as a value, just to kind of build some intuition for this. So the first thing that we said we can do with values is store them in variables, and we can do that with functions. So here we have this anonymous function that adds two numbers together, and we store a reference to that function in this constant called a. We can also have functions as property values of an object. So here we have this object called person, which is also a value. And it has two properties. One is called name, and the value of the property called name is Miyamoto. And it also has a property called getName, and the value of property getName is this anonymous function that returns this dot name. And effectively, that function becomes a method. So purely by functions being values and having the capability to store them as properties of an object, we sort of get the object-oriented programming for free, because we can just add methods to any object we want and then invoke them as methods and get the correct behavior. We can also store functions as elements of an array. So here we have this array called functions with 3 functions as its elements. And then we iterate over this array, the same as we would iterate over an array with any other elements. And then just invoke functions one by one, starting from the last one, and then passing the result of that particular function invocation as the input to the next function. Can anyone tell me what would be result after I run this? If I was to run this, what would be the result? So it calls the last function first with 1000 as a parameter, then captures that result, passes that to the one before, captures that result, and then passes that to the first function. So what do I get as a result? Hello 2001, because if we start with 1000, 2 times 1000 is 2000, plus 1, 2001, and then we get hello 2001. Thank you. Okay. And then we come to these last two. So all these ones so far are important and useful, but for now, I'm just going to park them on the side, and because I'm not too interested in that. What I'm really interested is this stuff. One, being able to pass function as a parameter to another function. So here we have two functions. One's called setInterval, which is a built-in function. And then we pass this function as a parameter to the setInterval function, the one that logs the current time. And if I was to run this, I'll see the current timestamp being logged once every second. And this is really interesting and really useful and really powerful idea, because if we think about functions as boxes, it's some sort of black box that you provide some inputs and then you get some outputs. What this allows us to do is to pass other boxes as inputs to other boxes. Yeah? So basically we can have boxes not working only on values as we're used to, like strings and numbers and objects and whatnot, but we can also have boxes working and operating on other boxes, working with other boxes. And we can actually explore this idea a little bit and look at something that you should all be very familiar with. Can you see the font? Is the font size okay? Yeah? Okay. Right. So, say we have an array of people, or a list of people, and then we have this function called getNames that takes an array of people and then returns another array, but only containing their names. If I was to call this getNames, what would I get as a result? Well, I get those three names, because those are the names of these three people. So we start with an empty array, and then we iterate over this array of people, and we just push their name onto this result, and then return this result at the end. You okay with that? Yeah? Okay. And we can similarly, we can have another sort of computation called parse, where we give it an array of strings that should contain numbers, and we then parse these strings into integers, and then just return an array of integers instead. So we started with an array of strings, and we ended up with an array of integers. And if we sort of inspect these two computations, the getNames and parse, we'll see that they're very similar to one another. They sort of share a lot of structure. Like the difference is minuscule. The only thing that's different is basically what is it that we are pushing. How do we encapsulate this rule as to what we are pushing onto this array here? And this is a place where we can use this feature that we can pass functions as parameter to other functions, and then do something like this. So we can start with an empty result. And then we can iterate, like so. And then we can push. And then we return the result. Okay. So now we have this box called map, but the box is configurable with another box. Like if we want to use this map, we need to pass another function as a parameter. Basically, the rule that specifies how do we transform the element of the original array into the element of the resulting array. And then we can implement these two functions in a much simpler way. We can say get names. And let's call this MyMap, just not to. Okay, and we get exactly the same result, because the function that we've passed in as a parameter would always extract the name property of this person. And similarly, we can do the same thing with as parse. So we can implement the parse too. What do we call these numbers? We call it inputs. Okay. And we get exactly the same result. So rather than having all this duplication floating around, we managed to create a reusable abstraction called MyMap, or map as it would have been called on array.prototype, that allows us to map one array onto another, to transform all the elements of the original array and then package them into another array. Okay. And then we can do the similar thing here, except that these two computations are slightly different. So here, we don't want to transform each and every element of the original array. We want to only include some of the elements of these arrays into the resulting array, only the elements that satisfied certain condition. And we can do this by implementing the filter method, what you normally do. So we can say array.prototype.filter is a function that takes function as a parameter, and then does what? Well, we need to check if when we invoke f against the current element of the array, returns truthy or falsy value. If it returns a truthy, then we need to push that element onto the resulting array. And then we can say, let's do numbers. Numbers. Okay, so we got exactly the same result. Whereas here we had all this looping logic that was very, very repetitive and same as above. We managed to make this way shorter by implementing this filter method, or myFilter, that just filters out the numbers that are odd. Yeah. But then, how about this? I'm going to show you a few more computations that can also be simplified and sort of deduplicated. So the first one is counting the sum of all the numbers in an array. So how do we do that? Well, we start with 0, then we iterate through the array and then just keep adding numbers up and then we end up with 30 as a result. Okay? If we want to compute the product of all the numbers, then the only thing that we need to change is the value that we start with to 1, and change this rule that specifies how do we combine the running result and the current element to get the new value of the result. So rather than adding them up, we now need to multiply them together. But apart from that, everything else is exactly the same. And we get whatever the result is. And we can do the same for min and max. Yeah? So min starts with infinity as the initial value, and then it just computes math.min of the running result and the next element of the array. Max starts with minus infinity as the initial value, and computes math.max of the result and the current element of the array. But again, all these 4 computations are very similar to one another. There's lots of duplication happening around here. So what we can do with this? What can we do with this? Well, we can build another abstraction and call it fold or reduce. So we can say something like this. We can say, well, now I need a method called reduce. Let's call it myReduce. But reduce would be slightly different. It would actually take 2 parameters rather than 1, because we need to customize what the starting value of this accumulator is, and what the rule is for how we combine the running value with the current element of the array. So we're going to call this reducer. Sorry. And then we'll just put this looping logic in here. And we can say we start with 0, and we iterate until the length. And then we just say accumulator equals reducer, accumulator this I. And we just return accumulator as a result. So basically exactly the same thing as we did up there. The only difference is that we sort of parameterized the rule as to how we combine these 2 values, the running result and the current element of the array, and what is the value that we start with. And then we can implement these functions in a much simpler way. So for example, sum would be something like this. What do we call these numbers? We call them numbers. Okay, so we got exactly the same result. We got 30, same as we did before, because we parameterized this reduce function with these 2 values. Initial value of 0, because when we sum things, we need to start with 0, and the rule that says the next value of the accumulator is obtained by adding the running value of the accumulator and the current element of this array. And we can do the same thing for product and min and max. So let's do product and min, and then we can stop. Actually, this is an interesting one. So I'm going to do this first. Okay, so we got 1. Okay, so this works the way we would want. We have the rule that does math.min accumulator and x, and we start with infinity. But is there a way for me to simplify this? Can we make this a bit less cluttered? Because there is something here that is a bit pointless. Okay, let's make a little experiment. I'm going to take this function, because this is a really sort of important idea, and it's one of the sort of things that is really annoying when you see it. Let's call this function xxx. Okay? So the function that we passed in as a parameter to reduce, we extracted it here, and we called it xxx. It's a function that takes two parameters and calls math.min with those two parameters. Okay? If I call xxx, I don't know, 1, 2, 3, 45, what will I get as a result? And if I call math.min, 1, 2, 3, 45, what will I get as a result? Same, okay. And if I call it with, I don't know, 1, 2, 3, and 4, 4, 5 as a result, and if I call this, get the same. So it seems that if I call xxx and math.min with the same combination of parameters, I would always get the same result, which means what? So if you have two functions that always produce the same result when you give them same parameters, what does that effectively mean? That it's the same function. We can just substitute one for another because it's a black box. We cannot tell how it does what it does. But if we observe that whenever we pass the same thing to one and the other, that we always get the same result, that means we can just substitute one for another, which sort of makes perfect sense because this function xxx does not do anything. It is just a sort of wrapper around math.min. It's just one extra level of interaction because whichever parameters it receives, it just passes it on directly to math.min, and whatever math.min returns as a result, that's what that function would return as a result as well. Yeah, it's just one extra box that does nothing. Yeah. So we can then go here and replace this with just math.min and get exactly the same result. And then we can do the same thing for, I need to call my reduce. Okay, and we get exactly the same result as before. By the way, can anyone tell me why did this not work with reduce, but it did with my reduce? I'm not saying that mine is better. Mine is actually not better, but it just happens to work in this case. Well, the reason is because the real reduce method is not really implemented like this. It's not calling reducer only with these two parameters. It's actually passing some extra parameters on as well. So I think here it would actually pass the index and the array itself. And that would break the math.min and math.max functions because if you pass 4 parameters to math.max, of which 1 is an array, you'll get none as a result back. So if we take this away, we get the behavior that we want. But with the real reduce, we won't be able to just pass math.min and math.max directly. Okay. So this was filter, map, and reduce. And we've seen these 4 different algorithms and computations and how we can condense them by using fold or using reduce. And it actually turns out that there is a kind of a special class or category for these type of computations, because you'll see that they all are very similar, because they all have this binary operation that has a neutral element. So if you ever heard about monoid, that would be an example of a monoidal structure, where you have the binary operation that is associative and has a neutral element. But what is interesting about this is that we can take this idea a step further. I'm just going to go back to this MyReduce and MyMap and MyFilter. If we sort of look into these 2 implementations of MyMap and MyFilter, we'll see that they also are very similar to one another. Yeah, there's also a fair bit of similarity between those 2 computations. So the question is there a way to implement filter and map by using reduce? Like, can reduce be used to implement these 2 in another way? So if I get this going, not sure why do I get 301 here and not. That's not what I'd expect. Okay, need to look into that. But let's implement this with reduce. So how would that look like? So we can say return this dot reduce. And then we need to pass in the reducer. So what should this reducer do? Well, it should get the accumulator and the current value. And then return this as a result. So we start with an empty array as the initial value of the accumulator. And then in each iteration, when we are reducer, we just append the f applied onto the current element of the array onto whichever elements we've collected previously. And that gives us the same result. And we can do the same thing, the similar thing for filter. We can also replace that with reduce. So we can say return this dot reduce accumulator and x. But then the logic is slightly different. Here we need to test what fx returns. If fx is a truthy value, then we need to concatenate accumulator and x. Otherwise, we just return the accumulator, and we also start with an empty array. Sorry. Where's my? Yeah. Okay. So that's where the filter is, and we get exactly the same result. 135779. And this is really interesting because it turns out that map and filter are just special cases of reduce. So it's actually reduce that's this magical spanner that you can use on arrays to accomplish any kind of computation or transformation of arrays. You can either condense an array to a scalar value, like a number or an object or something like this, or you can also convert array onto another array, either by mapping elements individually or by filtering them and removing the ones that don't satisfy particular conditions. So, map and filter, they just got their own special names because they are computations that are common. But again, they can also be implemented just as a simple usage of this reduce method. And that's why functions and reduce is a good abstraction because it's really, really versatile, and you can accomplish a lot with very little code. Okay. So the last bit about function as a value and about values is the capability of function being returned as a result of a function application. And this is a really powerful idea and a useful concept, because again, if we think about functions as boxes, this means that we can pass a box into the function and then get function to do something and then return another box, another black box as a result. So we have functions that actually operate on other functions, take them as parameters and then return them as results. And here we see like a really simple usage of that idea. So if I was to run this, I would create a logger for the name myService, and then when I call this log function, it's actually this anonymous function here that would be invoked, because that's what create logger function returned as a result. The create logger function is a box that returns another box as a result, which we can customize with this name here. So when I say give me a logger for the name myService and then capture the result, again, which is a reference to this anonymous function here, when I call log123, I get to see, myService 123, because this would prepend whichever name we passed here as a first parameter of the console.log. And this really is a useful idea. And I'm slightly running out of time, so I'm just going to show you a couple of scenarios where this might be very, very useful. So imagine we have a function, and let's call it sqrt. And it's basically just math.sqrt. And when we call it, we get 4 as a result. But then we can do this. We can say log is a function that takes a function as a parameter and then returns another function as a result. And in here, we obtain result by applying this function onto whichever x we pass in as a parameter and then return that as a result. And then here let's say just log x and result. What happens now? Okay, so we still get exactly the same result as before. So sqrt with log 16 returns 4. But we can also see that this 16 and 4 is being logged onto the console. So what this little log function did, or what it allows us to do, is it allows us to decorate any function we want. All we need to do is just pass that function as a parameter. And then we get another function as a result that would always invoke the function that we are decorating, but it would also, as a side effect, log the parameter that we passed in and the result that we got back. So we have a sort of non-invasive way of attaching this side effect of logging things onto any function we like. And I'm just going to show you one more for the end. Let's call this one memoize, which is also a function that returns function as a result. But this one is slightly different. it has this hidden local variable called map, and then it returns a function that does this. It first checks if this map has a property called x, or rather doesn't. And if it doesn't, then it stores f applied to x to map, and then returns map x. Okay. And then we can now say const sqrt with log and map equals, sorry, okay, I'm just gonna comment this out. And so now you can see that this still returns 4, which is the correct result. So the function still does the same thing. If I call it with 9, I'll get 3. Sorry, if I call it with 9, I'll get 3. And you can see that now we have two log statements being made, two logs being made, 16.4 and 9.9.3. Okay? If I call it with 16 again, I get 4 as a result, which is the correct result. But you'll see that there is no additional log statement, because this decorator here, the memwise decorator, is clever enough to work out that we've already invoked this function with these combination of parameters, stored that result in this map, and then just returned that as a result immediately, because there was no need to perform the same computation again. And this allows us to kind of add caching in a non-invasive way on top of any kind of function that we want. I guess I'll have to stop now. I run out of time. You've been great. Thank you very much, and best of luck.